the lesson you've all been waiting for. Logarithmic functions. So in this example, we're going to explore the inverse of an exponential function. So we consider the exponential function y equals 2 to the power of x. So if we explore this algebraically, to find the inverse of a function, we interchange the x and the y values. So if we do that with our equation y equals 2 to the power of x, what I get is x equals 2 to the power of y. And then normally we always write these equations as y equals. Do we have anything in our toolbox to bring y from an exponent down? Because I know that if I add something, I can do the inverse of subtraction. When I divide, I can inverse with multiplication. If I take the square root of something, the inverse of that is the square. So I have all of these inverses, but I don't have an inverse for an exponent. So the problem is I don't know how to isolate y. So right now we can't write this as a y equals. So let's look at this from a graphical standpoint. If we look at y equals 2 to the power of x graphically, so that's what we're going to do first. So let's not even worry about the rest of it. We graph y equals 2 to the power of x. And we did this in the last lesson, so you could even pull up the table of values. When x equals -3, I have 1/8, 1/4, 1/2, and 1, 2, 4, 8, and 16. So if you want to pause this for a moment, plot those points and draw that graph. So this is my graph of y equals 2 to the power of x. So now when I go to graph the inverse, remember with the inverse, the x becomes the y and the y becomes the x. So my y values are now my -3, -2, -1, etc. And my x values become the 1/8, the 1/4, the 1/2, the 1, 2, 4, 8, and 16. So again, what I would like you to do is pause and plot these points and join the points in a smooth curve. So now I have this line drawn in blue. And because these are inverses, they're a reflection about this mirrored line. And that mirrored line, or line of symmetry, I can find right there's my line of symmetry that reflects one graph onto the other one. So the equation of that line of symmetry is y equals x. So there has to be a way to write this as a y equals equation. If we can draw the inverse, I have to be able to describe this inverse using an equation. And right now, it's an actual function. So it's not even just that it's a relation. It's a function. Each input has only one output. So the inverse of this function can be determined by using a logarithmic function. So a logarithmic function is simply the inverse of an exponential function. So the inverse of an exponential function with a base of 2, in other words, y equals 2 to the power of x, becomes a logarithmic function that also has a base of 2. And we write it as y equals log base 2 of x. So in an exponential and a logarithmic function, or its logarithmic function, the bases remain the same. So note that the graph of y equals log base 2 of x is the same as the graph of x equals 2 to the power of y. But we write this equation, my logarithmic equation, rather than this inverse exponential in order to express the inverse of an exponential function. Because again, we don't generally leave equations as an x equals. We write them as a y equals, and it's that log that allows me to write it as a y equals. A logarithmic function has a base of b. The equation is y equals log base b of x. Y is the value of the logarithm, b is the base of the logarithm, and a is the argument of the logarithm. In the logarithm, the value of x has to be greater than 0. You cannot take the log of a negative number. It can be a real number, as long as it's greater than 0. The base has to be a number greater than 0 and not equal to 1. Because remember, if it's equal to 1, I'm going to have 1 to the power of x, which is just a constant function anyways. The inside of the logarithm is called the argument, and the argument can never be negative. So if we look at class example number 1, the graph of 2 to the power of x and x equals 2 to the power of y is shown. Write the label y equals log base 2 of x beside the appropriate graph. The appropriate graph is the inverse graph. So this is my y equals log base 2 of x. It is important that that 2 be written as a subscript and slightly smaller and below the logarithm. So if we complete the table, if I look at my first function, y equals 2 to the power of x, that's an exponential function. We just did those. The domains, x can be anything. The ranges, y has to be greater than 0. Oops, not equal to. Y is greater than 0, and y can be any value greater than 0. The x-intercept, there is no x-intercept because that's the asymptote. Oh, sorry, it is y equals 0. So the x-intercept is my asymptote, and the y-intercept is at 1. Or if I want to write it as an equation, it would be 0 and 1. Now, if I look at my logarithmic function, the domain this time, it does not cross the y-axis. The domain is all the values of x that are greater than 0. The range, I have negative range values. This is pointing me down, this is pointing me gradually up. The range can be anything. And this is true for inverse functions. The domain becomes the range becomes the domain. The x-intercept, it crossed the graph at 1. The y-intercept, it never crosses the y-axis. And the y-axis becomes my asymptote of x equals 0. So the table of values shown below are the coordinates of y equals 2 to the power of x and y equals log base 2 of x. The point 3 and 8 on the graph, on this graph here, indicates that 2 to the power of 3 equals 8. The similar point, although reversed, which is 8 and 3, on the log graph indicates that log base 2 of 8 is equal to 3. So what statement could be made from the point negative 2 and 1/4 on the graph of y equals 2 to the power of x? Well, the statement would be that 1/4 is equal to 2 to the power of negative 2. And then if I look at the point 16 and 4, which is this one right here, what statement could I make using the function? Well, the value of y is 4, so I get that 4 equals log base 2 of 16. we look at question C, we start to see some connections between exponential and logarithmic form. So the logarithmic form we get from this table here, and the exponential form we're getting from this table over here. So log base 2 of 8, that's how we read it, log base 2 of 8 equals 3, and 8 equals 2 to the power of 3. If I look at my log base 2 of 4, remember this is my x value, so when x equals 4, y equals 2. So log base 2 of 4 equals 2. And remember, in my exponential, this is the inverse. So my exponential function was 2 to the power of x. So if this is x, it now becomes y. And if this was y, it now becomes x. Because my logarithmic is y equals log base 2 of x. So if I go back up to my chart, log base 2 of 2, I look at where x equals 2. When x equals 2, y equals 1. So I get log base 2 of 2 equals 1. In my equation, my exponential, which is the inverse, that means that this x value becomes the y, and the y value becomes the x. So take a moment to fill in the last part of the chart, and then you can press play and see where we are at. So log base 2 of 1 equals 0, and then I get 1 equals 2 to the power of 0. On the next column, log base 2 of 1/8 equals -3. And 1/8 equals 2 to the power of -3. Then I have this exponent that is 1/4 equals log to the power, or sorry, not log. 1/4 equals 2 to the power of -2, which becomes log base 2 of 1/4 equals -2. And the last one would be written as log base 2 of log base 2 of 1/2 equals -1. So class example number 3 says, use the patterns developed from class example number 2 to write the exponential statement of 10 to the power of 3 equals 1,000 as a log. So the base stays the same, okay? What ends up happening is my exponent becomes the value of the log, and this answer here becomes the argument of the log. So if I have the log base 5 of 625 equals 4, how would I write that as an exponent? Well, remember, the base of the log becomes the base of my power. And then the argument, the value becomes the exponent, and the argument becomes the answer. So let's look at the characteristics of a logarithmic function. So logarithmic function is y equals log base b of x. The x-intercept is equal to 1. There is no y-intercept. I have a vertical asymptote that has an equation of x equals 0. The domain is the values of the x that are greater than 0, and the range could be any real number. The logarithm y equals log base b of x is equivalent to the equation x equals b to the power of y, where x has to be a number that is greater than 0, and b also has to be greater than 0 and not equal to 1. This b value is the base of both the logarithmic function and the exponential function. Since the logarithmic function is only defined for positive values of x, the logarithm of a negative number cannot be determined. And the reason why it's only defined for positive values of x is because that log was the inverse of our exponential function. And when I'm not transforming that exponential function, when it's written in the form of y equals ab to the power of x, it is always greater, or my y values are always greater than 0. So if the y values are greater than 0 in exponential form, it means that the x values can only be greater than 0. The logarithmic equation y equals log base b of x can be written in exponential form as x equals b to the power of y. The exponential equation y equals b to the power of x can be written in logarithmic form as log base b of y equals x. So I'll give you a moment just to digest that information. Okay, so here's a short 4-minute video about logs.
Time to saw up some logs. What? Seriously? You meant math logs? Really? Ugh, math is so lame. So today we're going to learn about how to go between exponent and log forms of an equation. Yay! Mind blow! Ooh, I know this! A base to an exponent gives you an answer. That's the be happy form. Alas, poor log. How are we to switch from yon exponential form into UF? Can you do me a favor and move these numbers in the exponential equation into their proper spots in the log form of the equation? I have a tea time at noon. I'd rather not be late.
So the base stays the base, the answer moves over, and the exponent is the new answer.
That rocks! That's right! The way to remember log form is to think of bacon and eggs. No, wait, please, just let me be a lumberjack. Wait, no.
Let's review what we've learned, how to go between exponential form of an equation and logarithmic form. In exponential form, we have a base to an exponent equals an answer. That's the be happy form. The rhythmic form is a log base of the answer equals the exponent. That's the log bacon and eggs form. Bacon and eggs form. That's it for now. Bye from Mathland.
So now if we take a look at the examples that are in your workbook, we look at class example number 4. State the inverse of the following functions and answer them in the form of y equals. So if we look at A, we have that y equals log base 3 of x. So in inverse form, this would become x equals log base 3 of y. Now, if I want to write this as a y equals equation, I have to go back into exponential form. So if I remember the be happy, the base, okay, or sorry, I guess would be bacon and eggs. In my bacon and eggs, I have bacon and eggs. This is my exponent. So I get 3 to the power of x equals y. If I look at b, if I want to write that in in inverse form, the x and the y exchange places, and I get x equals 8 to the power of y. If I want to write this into logarithmic form, the base and then x equals y. So what I end up having is the be happy. B-E happy. So in here, bacon and eggs. So the exponent and the eggs. So class example number 5 asks to convert each of the following from logarithmic form to exponential form. So what I'd like you to do is pause and try these 4 examples and then press play and see if you've got them correct. Okay, so if I look at the first 3, they should be fairly straightforward. 7 to the power of 4 equals x, 5 to the power of y equals 15, t to the power of m equals b. When I get to the last one, 5 equals 4 times log base b of 6. What I need to do is I need to isolate this log. I need to get it separated from the 4. So I divide both sides by 4, and then I get b to the power of 5/4 equals 6. So now what I would like you to do is work on class example number 6, writing each of the following as logs. So if we look at 6a, I get log base 3 of 64 is 4. B is log base 2 of 1/8 equals -3. C is log base e of f equals d. And d becomes log base a of 2x plus 4 equals 5. And it's important that that 2x plus 4 is written in brackets. So now if I look at class example number 7, it says calculate the value of t if log base 2 of x equals 3 and log base 2 of t equals x. So in this equation, I can't get x separated from the log. So what I need to do is rewrite it as an exponent. So the exponent becomes 2 to the power of 3 equals x, which would end up being 8. So then what I have in my second equation is log base 2 of t equals 8, which I can then write in exponential form. 2 to the power of 8 equals t. And that is equal to 256. Okay, I'm going to go through the last couple of examples because we've already done one like this when we have a logarithmic form of y equals a times b to the power of x. So we've looked at changing from the exponential form b to the power of x to the logarithmic form. What happens when we have that a? When we have that a, what we do is isolate the base. So we get b to the power of x by itself, and we move the a to the other side, and then we write it into logarithmic form. So I want you to try, the logarithmic form of y equals ab to the power of x would then become log base b. My answer becomes my argument, and then equals x. So the exponent becomes the eggs. So what I would like you to do is try class example number 8 and see how you do on those questions. So if we take a look at y equals 2 times 3 to the power of x, I would rewrite this as y over 2 equals 3 to the power of x. So as a log, I get log base 3 of y over 2 is now equal to x. The exponents becomes the eggs. For b, h over 7 equals 4 to the power of k, which means I would have log base 4 of h over 7 equals k. For c, take the r to the other side. T over r equals s to the power of p. So I I now have log base S of T over R is equal to P. And then when we get Y, when we bring the 3/2 to the other side, it becomes 2/3. So I get 2y over 3 equals 100 to the power of x. So I end up with log base 100, oops, not 1,000, log base 100 of 2y over 3 is now equal to x. In class example number 9, we're asked to go backwards, take the log and write it as an exponent, but then make sure it's written as a y equals equation afterwards. So we'll do class example A first, and then I'll give you time to do the next 3. So when we look at A, when I go to write this in exponential form, the base stays the same. The answer, or in this case, bacon and eggs, the eggs becomes the exponent, and the and becomes the argument. Or sorry, it becomes the answer. The argument becomes the answer. So now in order to get rid of this dividing by 3, I multiply by 3. And I get 3 times 7 to the power of x is equal to y. So take a moment to do the next 3 questions. Okay, so if we take a look at B, in exponential form, I would get 10 to the power of x would be equal to y over 4. So now I would have 4 times 10 to the power of x is equal to y. With C, I get 5 to the power of x is equal to 7y. Bring the 7 over and it becomes 1/7 times 5 to the power of x is equal to y. And then the last one is e to the power of x equals y over 5. So I now have 5e to the power of x equals y. So it's a heavy lesson going between logarithmic form and exponential form, but the key to remember is they're inverses of each other, so they allow us to solve for those exponents in a or in an algebraic manner. Okay, so your questions 1 and 2, 3 parts A, C, and E, 4 parts A, C, and E, 5 and 6, 7, 9 A and C, 10 A and C, and 11 to 15. You will get some class time tomorrow to work on this and to finish this up, but you should be trying to make use of your more time today.